welcome all to session 1BA. Welcome back, Matt. And I won't call it a follow-up session, but for those who attended the KICS and Kafka, we have, I think, a more in-depth study of queues and event streams. And please remember to fill in your feedback form after the session, and please post questions via the chat room. I know Matt monitors it, so I'll leave it up to him whether to answer at that moment or leave them to the end. So over to you, Matt.
Thank you. So good afternoon, everyone. So my name's Matt Lemming. I'm the architect for MQ for z/OS. And today I'm going to talk about queues and event streams, what they are, what the differences are, and obviously mapping those down into what that means when you look at IBM MQ for z/OS and Kafka. And in fact, really what I'm talking about here isn't a z/OS centric topic. This is something that applies to MQ on distributed as well. Okay, and like I say, like Melvin said, feel free to stick questions in the chat and I'll answer those to the best of my ability as I go along. So the basic idea here is that messaging is something that's been around for a long period of time. MQ on z/OS has been around for 27 years, as has the rest of the MQ product. And its reason for being has always been to connect applications together regardless of where they're running. And that's, you know, the need for connecting applications together hasn't diminished over time. All we are seeing is it growing, okay? So it used to be historically that your applications would run in on-premise data centers, maybe just in one data center or maybe in a set of geographically dispersed data centers. But they'd normally be owned by you, or perhaps you would be wiring your applications to applications running in with another business's application. So you'd be going across data centers. Now, of course, customers are in the cloud and their applications are running on different physical machinery in the cloud, sometimes again, all in the same data center or in multiple distinct data centers that part of the same cloud, or sometimes communicating across clouds or from one cloud back into on-prem. And all of these things are all about applications communicating to each other and needing to communicate in a reliable, scalable way. And the answer to that really is messaging. So messaging has grown significantly over time, and all of the predictions by everyone is that it's just going to keep going up. What has changed over time, however, is what exactly messaging is. Okay, so you know, the messaging of 20 years ago is no longer necessarily the same as the messaging of today, and that's kind of where this presentation comes in. And before I kind of go and talk about how messaging has evolved over time, I just wanted to say that you know, like a common thing, or one thing that seems to come up quite a lot is that customers say, well, I want to choose a solution based on its abilities. Has it got high availability? Has it got scalability? Has it got security? And is there lots of manageability of the environment? And if we're looking at MQ and Kafka, which is of course the point of this presentation, the reality is both of those scenarios, both of those solutions tick all four of these boxes, have done for a long period of time, and we have customers in both cases, multiple customers, you know, hitting the very high levels of availability, scalability, and security with both of these things. So actually, if you're looking to decide which solution to go for based on whether it's available or not, or scalable or not, that's not really a useful decision point. Okay, that's kind of something that isn't relevant because both of them solve it. So actually, you need to go and look at a more detailed level, which is really where you should be looking anyway. You know, the availability of something is not always the most important thing. What is important is how are you going to use it. Okay, and that's where you should be you know, going for your decision making. Okay, but it does require you to understand a little bit more. So there you go. So I'm going to talk about a couple of patterns, and this first part of the presentation is a bit relatively high level. Later on, I'm going to go in much more detail. And I should also say there's actually quite a lot of presentation here. So there's a chance that I might not get through everything in the 1 hour we've got allotted. But the idea here is that the slides should be fairly self-contained. So if I don't get all the way to the end, then feel free to kind of use this as a reference point. And if not everything makes sense up front, again, refer to the slides and feel free to reach out to me as well to ask questions later. So, you know, if you're looking at messaging, then there's kind of architectural patterns and application patterns. And I'm going to start off with the application patterns first. And at a course level, there's kind of 3 main application patterns. So starting from the left, and this is kind of the one that's been around longest, is the idea of critical data exchange between systems. And those systems can be close together or they can be far apart. And those systems might be owned by a single organization or they might be owned by multiple organizations. But regardless of that, the key thing is you want to exchange data from one system to the other in a reliable way so that that data always gets through, gets processed, and there's some form of acknowledgement that it gets processed. Now, that doesn't mean that it has to be processed straight away. It just needs to be processed, you know, within some form of SLA, right? So that might be, you know, seconds or minutes or whatever. But the key thing is it gets processed eventually. And then obviously things like security and all the other stuff come with that. Then there's this middle one. So this one is, again, been around for a while, but not as long as the critical data exchange model. So here, and this is, you know, historically, this used to be most often thought of as pub/sub or publish/subscribe. A more modern word for it is actually real-time eventing. And so the idea here is that your systems, as they run, they generate events indicating the current state of the system. And those events will are of interest to a set of applications that need to process them. And there may be 0 applications interested at that particular time, or there may be many. And the idea, you know, the real idea here is events are generated, they're consumed by those applications that need those events, and that number may scale up and scale down over time. And the system, the messaging system, kind of deals with that scaling up and scaling down. The applications don't have to worry about it. And then we move on to the most recent model here. And I'm not going to, I almost said more modern. This isn't, so it's more recent. It isn't necessarily a more modern way, because that implies the patterns to the left are no longer valid, and that's not true. This is a new evolving approach for messaging, but it's for a specific set of purposes. And so, you know, the middle box talks about events, you know, individual events. Each individual event is important. The right-hand side is more like, well, actually, those individual events aren't important to me. What is important is if I look across that whole set of events and see how a system or a set of data or whatever it is evolves over time. That's what I'm interested in. It's not the point in time view, it's the evolution of the environment and caused by that successive set of events happening over time. And this is where event streaming comes in, because from an application, if you're processing this set of events, there's like a real-time stream of data coming in, and applications walk over that stream in order to do whatever processing they need to do, whether it's AI or something like that. And this has its own set of requirements as well. You know, individual events are probably quite small, maybe a kilobyte of data or something like that. If you're looking at lots and lots of these over days and weeks and maybe months, then you've obviously got lots and lots of data being generated and probably aggregated together as well. So this has much higher data requirements than the other two patterns on this slide. So that's the application patterns, and these really are quite high level. And we'll come back and map these onto the MQ and Kafka products in a minute. There's also architectural patterns, which I guess is probably something that people haven't thought of as much. But actually, when you think about it, there really are quite clear architectural patterns here. Messages and events are really communication, okay? And that's particularly clear with messaging, where you're sending data from one endpoint to another. But events is communication as well. Each individual event is the communication of something from one application to a set of other applications. Okay, so that's a clear grouping together of those sets of capabilities. And obviously, communication isn't just inside a small range of applications. It can be across a single business, across multiple businesses, across the whole world. Whereas the event streaming view of things, actually, we kind of get away from this idea of communicating individual things that are happening. And actually, we're kind of looking at something that's a bit closer to a database, right? There's all these stream of events coming in. That's basically a vast amount of data. Traditionally, that might have been held in a database and might still be being held in the database. But actually, this is somewhere in between messaging and actually holding data for some period of time for being processed. Okay, so it's kind of a little bit of a blurry line, and that's quite an interesting way of thinking about it. And the reason that's important, this idea of data persistence for a period of time, but not forever, which is where database is coming in, is actually when we go into the nitty-gritty details, you'll kind of see this, long-term data persistence rear its head again and again. So let's start looking at this in a bit more detail, because this idea of these different patterns actually have to map down onto particular products. So if we start with the application pattern view, on the left-hand side, we've got IBM MQ, and on the right-hand side, we have Apache Kafka. And I'm going to start with the extremes, okay? So if you want to look at critical data exchange, okay? So the idea that each individual message sent is something that needs to be processed in a particular time boundary and processed exactly once and then done, you need a set of criteria, a set of capabilities on the messaging infrastructure to do that. And this is where MQ will, really has its reason to be, right? This is what MQ is optimized for. So we have once and once only delivery with persistent messages and transactions. And we also have very fine-grained addressability of the messages, in that we can have lots and lots of individual queues, and you send a message to a very specific queue, and you might have tens of thousands of those, depending on what your application needs are. But MQ is very optimized for this critical data exchange approach. It's not something that Kafka is optimized for, right? So you might be able to do something a bit like this, but you will be spectacularly outside of the sweet spot for Kafka, to the point where actually it's not a good idea. So if you want critical data exchange, really that's MQ. On the other side, flip side of the coin, Apache Kafka, right, is really, really optimized for event streaming. Okay, so we've got this idea of lots of consuming applications being interested in that data, and when there's a lot of data, you have to be very, very optimized with how you manage that vast amount of data. And Kafka does just that. It doesn't duplicate data in the way that MQ does. Okay, and again, we'll come back to that later. And it also has this idea of a stream history. Again, that's something that Kafka has, which IBM MQ doesn't. So if you're looking for event streaming, then Kafka is definitely the answer, okay? And I'm trying to be fair here as well. I do obviously work on the MQ product, but there's definitely cases where one is way more obviously as a thing to use than the other. And then there's an in-between point, which is where it kind of gets a little bit hazy. And that's the eventing side of things. So as I said, event-driven workloads is a kind of a common term today, but 5-10 years ago, that would have been pub/sub, okay? And MQ has supported pub/sub for a long time. And it does it in its own way. And in reality, that kind of maps down eventually onto MQ queues. And again, we'll talk about that later. But Kafka also does event-driven and can, easily be used in that space as well. So there's kind of, if you're looking at event-driven, then it really kind of depends on exactly how you want event-driven to be done as to whether you go with Kafka or MQ. Okay, so there's kind of this nasty little blurry bit in the middle, but then there's obviously very obvious use cases for MQ versus Kafka on the side. The architectural patterns is a much more obvious sort of line between one and the other. Okay, communication is really where MQ excels. Okay, it has been, for the last 25 plus years, customers have had MQ across their entire infrastructure and multiple data centers, moving data back and forth. okay, and having a collaborating but loosely coupled set of queue managers moving messages back and forwards between their applications. MQ has done that for years. Kafka doesn't do that communication pattern. It's really much more data centered, based on keeping data around for a relatively long period of time and efficiently serving it up to applications, okay? And that is a completely different set of capabilities, one which MQ doesn't really have. So, and now I'm going to reiterate the fact that regardless of where you are on this picture, both MQ and Kafka still tick all the management, availability, scalability, security options. So they're there, but really you don't need to care about them when deciding which one to choose. What you make your decision point on is you know, the bits on the top of this picture. And actually, in reality, you probably need to go down and an extra level of detail, and that's where we're going to go. Okay. And that's going to be where the rest of this presentation is, looking at the next level of detail, because that's really what you want to understand. You know, don't believe the hype when you say, you know, Kafka is a perfect solution for everything, because it's not. It depends on exactly what you want to do. It's a good solution for many things. It's not a perfect solution. A one box ticks all solution. It's not like that, just like MQ isn't. So I'm going to, you know, the next set of slides are going to look at compare and contrast MQ and Kafka based on their differences, and also in some cases their commonalities. Okay, so we're not just going to be looking at differences, but actually we're going to be making links where maybe the terminology is a little bit different, but actually the capabilities, once you ignore the exact words, are very, very close. And often those differences are what, you know, that those terminology differences are what people focus on, when actually they're irrelevant. It's what the capabilities are, and that's kind of what we're going to talk about now. So let's start off with message consumption, because this is kind of the easiest bit, and we're going to start talking about consumption models first. So, you know, if you've looked at MQ or Kafka at all, you'll probably really be aware of this particular difference already. So let's start off with destructive consumption. So the idea here is that your data is being stored by the messaging system, and then as a consuming application starts to get it and process it, that action of processing the data results in the data being deleted from the messaging system. Okay, so we've got a consumer, there are 8 messages on a queue or topic or whatever you want to think of the set of data is actually called, but as the consumer gets the data and processes it and walks through it, that delayed data is deleted from the messaging system. Okay, and that means that over time, while new data may come in and is then taken out, actually the amount of data stored at any one time in the messaging system is normally relatively small, okay, because there should always be something consuming that data. That doesn't mean there aren't periods where actually it builds up quite high, but in general, over time, you'd expect that set of data to be being stored is relatively small, because there's always someone getting it and processing it. However, messages stay in the messaging system till they're consumed, and it's the application that controls when they are consumed. Okay, so the application, until that comes along and gets a message, the message is not going to go anywhere else. It's only there. It's there until the application gets it destructively and is done with it. And you know, if something goes wrong and the consuming application no longer is available, then there's the potential for space to fill up, which might actually result in more data coming in, no more data coming in temporarily until more space is freed up. Non-destructive consumption is obviously the total opposite of that. Consumers never delete messages. They effectively read the message and they read it into their own memory, but the message is still in the messaging system. Okay, and that means that that consumer can go back to the start if it wants. So here it's consumed, you know, all 8 messages, but for whatever reason, there might be a need to go back to the start. And you can do that repeatedly. You can always go back to the start, even as new data is coming in. There's always the interesting question about, well, how do you know where to start? Do you start from the beginning of time, or do you start halfway through? And how do you know to go halfway through? And I think probably what happens most times with replaying messages, you either go right back to the start and have to incur the cost of going and processing everything from the dawn of time, or you go and read just from the end and just pick up new data, but you do have the capability of, you know, reading back from the start as many times as you want, because the data's never been deleted by the application. That said, you know, there is no such thing as infinite storage, because all this data is being stored now independently of the application. At some point, there's going to be a need to throw away old data so that more data can come in. And this is where the messaging system provides that pruning of data, okay? So the messaging system decides when data is no longer important based on some rules, which might be time or amount of storage consumed or something like that. But that decision is done by the messaging system and not the application. And you know, if those messages haven't been consumed by the application, well, that's just tough. Okay. Now, and you know, hopefully, if you've looked at Kafka MQ at all, it's obvious that the left-hand side is MQ and the right-hand side Kafka. So a different view of consumption is actually how many things can consume that data. Is it exclusive consumption or shared consumption? So again, starting on the left, exclusive consumption basically means that there is a single consuming application thread getting that data, okay? And it gets the first message, the second one, blah, 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 up until there's no more available messages. And because it's exclusively consuming, there's a single thread consuming that data, that means you get an absolute order of message delivery. You see the first message, the next one, the one after that. And if there is a history involved in a particular sort of time sequence that's relevant to the consuming application, they can work based on the guarantee that they've got this data in that time sequence. However, because there is a single consumer, that does mean there is a limit on scale. Basically, those messages can only be consumed at the speed that single consumer can go. That doesn't mean you can't get high availability of the consumer, because you can have one active and then multiple passive consumers ready to come in if the single active consuming instance fails. So, you know, there's definitely no need to say this is a single point of failure. However, it is a point of scalability. You know, it's a bottleneck basically. Shared consumption, again, is, you know, it's got a number of different capabilities. So here we're talking about multiple consumers working together, collaborating together to consume the data from the messaging system. And they each get some subset of the data in that messaging system. Okay, they never overlap, but they instead, you know, that data gets partitioned between them, probably just in the order in which they pull the data off the system. And because this is very dependent on how those consumers are running and when the next one tries to get the next bit of data, you're almost guaranteed that you aren't going to get any message ordering, okay? Or certainly not reliable messaging ordering over time. It does, however, scale nicely, right? We've got 3 consumers, so you can scale 3 times as fast, or 3 times as much as the picture on the left. And if you wanted to scale further, you just add another consumer, and he gets another subset of those messages. You've also got improved availability here, because if a single consumer fails, then there are still other available consumers processing at that particular point. Okay, so, you know, if one of those goes, then you still got 2/3 of your consumers available. So actually it's much more improved availability from the picture on the left. But that doesn't mean the picture on the left isn't highly available. And then another, and this is perhaps slightly more subtle, is actually how do you confirm when you've received or produced that data? And there's kind of, again, 2 models here. Application control confirm. Again, this is very, you know, the application is in control here. It gets its bit of data and it decides when it's going to acknowledge that it's received and processed that data and pass that information onto the messaging system. So here, the consumer's received message 0 and then it acknowledges it. And then message 1 acknowledges that. And basically each time it gets a message, it does something with it and then acknowledges it to the message system. Now it could do that, or it could also just acknowledge them in batches. Either approach works, but the key point is it's the consumer who decides whether they've processed it or not. It's not the messaging system. And once you've got this consumer controlled acknowledgement, you also, you know, which we normally call a commit, And then, of course, there's the rollback aspect of that as well. You also have the ability to coordinate that with other pieces of infrastructure, whether that's databases or whatever. Okay, so you get proper transactional processing. And it's these set of semantics, application control confirm, which allows the application to know that their data has been sent exactly once, and not at most once or at least once, but they know it's been sent and have been processed in a reliable way. However, this approach where the consumer's in control means that it needs to tell the messaging system when that data has been processed. And so that means there is more chat going on between the consumer and the messaging infrastructure, which means that there's a bit more overhead there. And the exact amount of overhead does depend on the model. Like if you're consuming it, if you're confirming every individual message, that's obviously more expensive than if you confirm the first 4 and then the next 5 in batches. Asynchronous confirm is a completely different model. It's kind of flipped on its head. And here, typically, it's not the consumer itself doing the confirm. It's either the messaging system or the client libraries provided by the messaging system doing that confirmation. And so, often this is a timer-based thing. So the consumer is sitting there processing messages, and periodically the messaging libraries, i.e. not the proper consumer itself, has a timer pop, and when that timer pops, it will go and confirm all the messages received by that consumer. So there's kind of a decoupling of control here. And the nice thing about this approach is, one, the consumer doesn't have to worry about it, and 2, it is more performant, right? Because the consumer and the consuming libraries and the messaging system can work together to kind of batch this workload up in an efficient and more performant manner. However, because the consumer is no longer in control and things are done in a sort of more of a heuristic manner, it does mean that you've got potential, if something fails, to have to do a certain amount of reprocessing. Okay, so that means messages might get processed twice, or might get you might end up inserting things into a database twice, and often that's something that the consumer application has to be aware of. Okay, so it has to think about the fact that it may need logic to deduplicate data if necessary. Okay, so now let's sort of take that set of thoughts and try and match them against MQ and Kafka. Okay, and the boxes here with the star against them, I'm going to go back, I've got too far, are the ones where this is a particular sweet spot for a given solution. Okay, so destructive consumption, if you know anything about MQ, if you get a message, it's destructively got, okay, under a transaction. Okay, so this is what MQ is incredibly optimized for. We will look after them until a message is gotten by an application or they're expired. So that's a sweet spot for us. Kafka doesn't do destructive consumption, okay, at all. It's not something that Kafka doesn't make sense with it. Non-destructive consumption, this is something where Kafka excels, okay? Data is stored on Kafka topics, messages are stored on Kafka topics, and those messages are stored there independently of how they're being consumed and processed by applications. And Kafka itself decides how long to keep that data based on configuration, whether it's keeping data for 7 days, which is the default, or perhaps saying, well, actually, this topic is going to take up, I don't know, 0.5 terabyte on disk, and if it gets past that, I'll start throwing data away. Okay, but that's the sort of level of control you get in terms of keeping data around. It's that sort of granularity, nothing to do with the application at all. MQ can do non-destructive consumption in that you can go and browse messages on a queue. However, it is not best practice to keep messages on the queue for a long period of time and browse the data from them multiple times. Okay, that's not a sweet spot for MQ. You can do it, but it's really it's not what we're optimized for. That doesn't mean customers don't have whole applications built off this. They do. It's just not really an optimized path for MQ. MQ is optimized for getting data in and getting it out relatively quickly, but buffering it up if needed. Okay, keeping lots of data inside us is less efficient because you kind of have to page it out to disk and all that sort of stuff. So if we look at exclusive versus shared consumption, again, we've kind of got a different set of things here. So this is that. Okay, so MQ supports both of these, exclusive consumption and shared consumption, and we have done for many years. Okay, shared consumption is probably the solution sweet spot from MQ perspective, because it gives you much better scalability, as we spoke about, and also it's way more efficient in terms of the way we manage our data and the way we log data on disk. Okay, Kafka is kind of really all about exclusive consumption if you look at individual consumer groups, and this is where I'm going to kind of defer some of these thoughts until later on. So there's no idea of shared consumption of a topic partition in a Kafka consumer group. So we're going to come back to this. Really, we're talking about exclusive consumption in a Kafka model, but that's kind of a subtle point, which we'll come back to later, so kind of bear with me on that thought. And then in terms of confirming things, both options work for both solutions. However, application control confirm, the ability to go and do an MQ commit or commit an XA transaction, is a much more natural model for MQ. We tend to give immediately, anytime you call any MQ API call, we will tell you whether it worked or not. Okay, so we give immediate feedback and you can immediately know whether something's worked or not. You can do that with Kafka if you tune Kafka away from its defaults and away from its performance sweet spot, but really you shouldn't, because you're kind of getting out of what Kafka is perfectly capable, really designed to do, but you can. And again, the situation is inverted when you look at asynchronous consume, okay? So, sorry, asynchronous confirm. MQ allows you to asynchronously confirm stuff, but it's only supported on a subset of our API, and it's really a performance optimization rather than an architectural model. Okay, so it's possible, not something that lots and lots of customers really worry about as a decision point in terms of how to design their applications. With Kafka, however, asynchronous confirm is entirely the sweet spot, okay? And that is something that applications need to be aware of as well, because it affects how they consume data and how failures and retrying data, retrying sending of messages happens. So as an example, the default is that messages are only confirmed every 5 seconds based on a timer, okay, when you're consuming a message. And if messages are being sent, then that send, if it fails transiently, then that failure is retried under the covers for up to 2 minutes, okay, before that gets reported to the application. So it's very asynchronous, and the messaging layer, i.e. Kafka, hides that from the application by default. Quite different from MQ, whereas if you try and send something and that send fails, you'll get told about it, and then you can decide whether to resend it or not. Okay, so really big difference here, really important. And it does inform how you write your applications. Okay, so these are critical points. So queues and topics. This is obviously an important section. So queues, I'm sure everyone here probably already knows, this is really about one-to-one communication. You have a set of producers sending messages onto a queue. Each producer sends a message, and that message gets consumed by one consuming application, which processes it, and then that message is gone. Okay, so one-to-one. And this is really something that only the MQ supports. So we're going to kind of ignore that from now on. We're going to talk about topics. Now, topics is one-to-many. The idea here is that you have a set of consuming applications who are interested in a particular topic, and they register this interest by something called a subscription if you're talking about MQ, or just they have a way of registering their interest in a particular topic, and then producers publish or send data to that topic, and it gets each consuming application gets access to that data on the topic if they're interested in it. And that set of interested applications can evolve over time. So it might be that no one's interested for a period of time, or it might be that one application is interested at a time, which is kind of a bit close to a queue, but different. Or it may be many applications. But the idea here is it's 1-to-0, 1-to-1, or 1-to-many is all of those capabilities are possible with topics, and then every consuming application gets to see the data. Okay, so there's no sharding of data between consuming applications like you get with a queue. So let's look at this the next level down. Okay, so both MQ and Kafka have topics, and they both provide this one-to-many semantic, but the way they actually do it is quite different. Okay, with MQ, the topic is kind of quite a lightweight thing. It's something that you can administratively define if you want, or you can just kind of bring it into being very ephemeral, in an ephemeral way. So it's kind of transiently existing for while producers come in. And it's not a place where message data is stored. It is a matching layer. Okay, it's a thing that says this producer is generating information that's of interest to these consuming applications. And so consuming applications register a subscription against the topic, and that subscription decides what set of messages they get. And a subscription MQ is always associated with a queue. So the data from the topic that gets matched to the subscription is stored on a queue, and then the consuming application goes and gets those messages off that queue, and they get their own copy of the message. And this is really, really important. Message duplication is going on here. So if we've got 5 subscribing applications in MQ, one message gets published, 5 copies of that message get sent, one to each of the subscriptions queues. And so that means, the more subscriptions you have, the more message copying is done, and the more work MQ has to do to make that happen. And the other thing here is actually these topics, because they don't really store data, they are very dynamic, fine-grained, and you can have a lot of them. Okay, hundreds of thousands of topic strings dynamically matching from consuming applications. So it's very, very dynamic, very lightweight, and it's very flexible. Kafka topics, obviously the terminology is the same in that you have a topic, and actually in Kafka, really a topic is sharded into a set of entities owned by individual Kafka brokers, and those are called topic partitions. So you have this idea of a topic which is split into coherent sets of data, and that coherent set of data is a topic partition. Okay, and producers send into a topic, which means that the data they're sending, the messages they're sending, go to one particular topic partition somewhere in Kafka. And the topic partition stores that data on disk. Okay, so a topic in Kafka is not lightweight like it is in MQ. It is a thing with real resource behind it. It might have terabytes of disk for each topic partition, because it's a thing where all the data is being stored. And a really significant difference, other than the fact that topics are actually a really big physical thing, is the fact that each consumer, and here we talk about consumer groups, which is a set of collaborating applications as a single entity, goes and consumes the messages, or I shouldn't say consumes, actually go and read the messages from that topic partition. And if you've got multiple consumers groups, they will all go and read the same data. They don't get their own copy of it. Okay, the same data is held in the topic partition, and they all see the same data. Okay, and what that means is Kafka has to do less work as the number of consumer groups go, because there's always one copy of the data. It just gets served to multiple consumer groups. And if you add another consumer group, that's just taking that existing data and sending it to them as well. But there's not lots and lots of data being held on disk individually. There's one copy of the data on disk. So the fact that topics are a bit more heavyweight on Kafka means that there's actually a limit, a more fine-grained limit to the number you can actually have. And so across an individual broker, so an individual running instance of Kafka, the maximum number is around 2,000 to 4,000-ish. Kind of depends on your capability, but quite different from what MQ's got. So, if you need lots and lots of fine-grained topics that evolve over time, MQ is a better match. If you've got coarse-grained topics that you need lots of people to efficiently consume data from, then Kafka is often the better match. Okay, so that's the application view of things, and we will come back to consuming applications a bit more later. let's talk about scale for a little bit. And this is often an interesting point, because we've heard lots and lots of customers say, oh, Kafka's way more scalable than MQ. MQ does things in stupid ways. You've got single queue managers. And I think that's really a terminology problem. And it's not a fair comparison of how things work in MQ compared to how things work in Kafka. Okay, so Kafka has a set of brokers. Brokers are joined together in a cluster, and they collaborate to allow messages to be sent between producers and consumers. And the scaling is done by having lots of brokers. Okay, in MQ, we have individual running processes, and they're queue managers, right? A queue manager is basically the same as a broker, and a single queue manager and a single broker can only scale to so far, and there basically becomes a point where that can't deal with the amount of data going through it. It's the same for Kafka, same for MQ. So both of them, to scale and become highly available, you actually need to spread them out over multiple running instances. So MQ does that via having a cluster, or more recently a uniform cluster, or if you're on z/OS, it has a queue sharing group. Kafka has clusters. Okay, so if you hear Kafka cluster, don't go and say, oh, there's no equivalent of that in MQ. There is. It's a uniform cluster, a queue sharing group, or a normal cluster. And then other things that are, it's useful to kind of make sure you understand the right semantics is, so I've talked about the idea that Kafka has topics that are sharded over brokers, and each of those shards is known as a topic partition. In MQ, if you've got queues that are sharded over multiple queue managers, that's known as an instance of a clustered queue. Okay, so you can have an MQ cluster, and you can have an individual queue called Q1, and that can be spread over the whole uniform cluster, and messages get split, sharded amongst those available queue instances. That's exactly the same as what happens with a Kafka topic partition. And then what you have is you have applications consuming from those clustered queue instances and spreading the work to give you scalability and high availability. And on the Kafka side, you have a consumer group. Okay, so the model, while the terminology is different, actually the reality is it's a very, very similar model, and that often gets missed. So let's look in a bit more detail, just where that I'm running a little bit tight on time, at how consuming works with Kafka. Okay, so I mentioned that topics are sharded into partitions. So this picture shows a single topic sharded into 3 partitions. Okay, so there's 3 brokers in this Kafka cluster, each get their own partition of the topic, and the messages sent to those partitions are different. Okay, so if that producer up top left hand side sends one message in, that message can go either on partition 0 or partition 1 or partition 2. It doesn't go across all of them, it goes to exactly 1. Okay, and the decision as to where it goes is dealt with via Kafka. By default, it will round robin them, or there is a way of actually selecting a particular partition based on something called a key, okay, which is hashed down to a particular partition. So in terms of producing this data, that's round robin or possibly selectively sent, but either way it's distributed amongst those partitions. To consume data in Kafka, you have a consumer group. Okay, and a consumer group is a set of related processing application threads. Okay, it's not a single thing by itself, it has a set of threads that are associated with it by having the same name, effectively a group ID. And here we have 2 consumers making up that consumer group. Okay, and with Kafka, the consumer group always gets the ability to read all the data from all of the partitions of a particular topic. So that a consumer group is reading from this particular topic, and there are 3 topic partitions but 2 consumers. That means one consumer gets 2 partitions, and the blue one at the top just gets the blue partition. Okay, so there's always this mapping, so that if you've got less consumers than you've got topic partitions, one or more of those consumers will get multiple partitions to consume from. But an important point is that a partition is only ever consumed by a single consumer in a consumer group. Okay, so you never get the case where like the blue partition goes to the top consumer and the bottom consumer. That's not what happens. So if you want to scale, and when they're consuming, sorry, I should say this, when they're consuming from a partition, the data on that partition is read out in order. Okay, so you get guaranteed messaging order on a partition level. Okay, and you can have less consumers than partitions, as we see in this picture. If you were to add a new consumer to this picture, then what happens is Kafka will rebalance where partitions are sent to, and actually spread them out so you've got an even flow. So each partition in this case is being consumed by a single consumer in the consumer group. However, if I were to add another consumer, that consumer will not get to consume data from a partition, because you can only have a single consumer in the consumer group connecting to a partition at any one given time. So the only value of having this spare consumer here is if one of the other ones fail, in which case Kafka will detect that and then connect that partition to the currently idle consumer. And then there's a whole load of magic that happens under the covers by Kafka that actually maintains state about the consumer group as a whole. So you can see here, we've got these offsets here. We've not really talked about offsets, but basically the offset is where in the partition that consumer has last got a message from. So this blue one's managed to read right to the end of its partition. The red one's got to the end of its partition, actually the same for the green one as well. But that information is kind of stored on a per consumer basis and stored inside Kafka. Okay, in a single topic partition. Again, we'll come back to that point. In fact, I'll mention it now. The idea here is that these things are stored, but they're actually stored in a single place, which is actually a potential bottleneck in terms of performance and single point of failure. So let's look at the MQ view of things. So again, from a producing side, so here we're talking about clustered queues, okay? And for a given cluster queue, if you've got multiple instances of that queue in a cluster with the same name, then MQ kind of will distribute work across that set of collaborating queue managers. And so that means when producers send messages to that clustered queue, those messages get shared across the available instances, just like they do with Kafka topics. And that decision is made by basically a round-robin set of decisions in the sending queue manager. So, but for the moment, let's just assume they're evenly distributed amongst the available instances of the queue. So in terms of consuming this data from an MQ application perspective, again, your application is made up of a set of collaborating consumers, okay? And those consumers connect into MQ and connect to a very specific queue manager inside that cluster, okay? And I think it would be fair to say that this is an area where Kafka has made it simpler than MQ has. However, uniform clusters, which is a more recent capability, do make this connecting into MQ and getting connected across the whole set of clustered queues much, much simpler. Okay, so that's kind of no longer a decision point really if you've got uniform cluster capability. But anyway, individual consumers consume from a particular instance of a cluster queue, just like particular consumers in the consumer group consume from particular topic partitions in Kafka. What we don't have with MQ is the idea that if you've got two consumers and three instances, then actually two of those instances go to a particular consumer. We do not have that. So with MQ, you want to have at least as many consumers as there are instances. So here we're adding in a green consumer, and now all of the instances are having their messages consumed. Okay, and again, message ordering is only based on the individual instance, but actually there's not lots and lots of message ordering inside clustering, because there's both a fanning out of message data and then a individual consuming on the right hand side of message data. So it doesn't have quite the same ordering semantics that you get with Kafka. However, one other really interesting point is that we can scale further. So here we've got an equal number of consumers processing that data. If these consuming application is starting to be a bottleneck, you just add more. Okay, and because MQ queues can be consumed by multiple applications at the same time, then we can scale better. Okay, so now you've got two things consuming from the blue queue instance, three things consuming from the red queue instance, and 2 from the green queue instance as well. So we can scale up much more efficiently by adding more consumers, which is something you can't do in Kafka. You can only have this one-to-one mapping at most. So let's kind of try and summarize this. There's basically 2 scaling points to consider here. There's scaling of the messaging infrastructure, if that becomes a bottleneck, or there's scaling of the consuming application, if that becomes a bottleneck. and both of these are possible with MQ and Kafka, but they're they've got kind of quite different approaches, okay? With MQ, it's trivial to scale the number of consuming applications. You just start up another application, and right, you can scale it up, start up another application when demand gets high, and you can scale it down as demand is, the amount of data is less. And that's trivial, and we've got examples of things like Keyless autoscalers that do that. With Kafka, it's much harder. And the reason for that is you can't scale past the number of topic partitions. If you've got 3 topic partitions, then at most you can have 3 things inside a consumer group processing those topic partitions. So actually, the topic partition number is your scaling factor, and is, if you need to go past what you planned in advance, then that's tricky, okay? So really, the advice is plan in advance with Kafka to get the number of topic partitions you think you are going to need for the foreseeable future from a scaling perspective. Now, you can add other topic partitions, but actually it's quite an involved process. And when you add another topic partition, you start to lose the message ordering that you get, or event ordering that you get with Kafka. So, MQ, scaling applications, is trivial, totally trivial. Kafka, totally doable, but requires a bit more thought and isn't as trivial, okay? It's not something you can scale up and scale down really, really easily. MQ, you absolutely can. If your messaging system is a bottleneck, then again, obviously you need to start looking at scaling that out. And again, this can be done with both things. So with MQ, that's a question of adding another queue manager, defining a set of new cluster queue instances, and then MQ will automatically start balancing new messages and new consumers against them. And that's, that act of, adding new messages is, new cluster queue instances is actually quite trivial, because they come along, and because MQ doesn't need to store state here, because there's no idea of a history of messages, that new queue manager and new cluster queue instances just come along and they're empty, and messages will add to them over time. So that's really quite a quick thing to scale up. Scaling down is a little bit more tricky. You need to drain messages, but it's not that hard. So scaling up is easy, scaling down a bit more complicated, but not that hard. Kafka, it's different. So you can add more broker nodes to your cluster, absolutely, right? And that's not a hard thing to do. The tricky bit comes into how do you redistribute the topic partitions across those nodes to make sure that actually you've got an even spread of messaging. And doing that itself requires a little bit of thought, but also because there's a set of state associated with individual partitions, you have to make sure that the new brokers have access to the history, that existing state in that partition. And so you have to move data around, which can take time. Now, to be fair, they've got ways to do it using things like tiered storage, but it's not as simple as it is with MQ, but it is doable. And there's some references in the bottom left-hand side describing how to do that. So feeling that I'm going to run out of time here. So availability, again, both of these things do that, right? Now, MQ and Kafka both are highly available, have been for years. They all rely on replication of the individual queue managers or brokers, and they have this idea of leader and follower patterns. So a broker or topic partition can be replicated amongst multiple brokers, and one broker will be the leader for that topic partition. And if that broker fails, then another broker will become leader shortly afterwards. With MQ, you can have, queue managers are the points that get replicated, and you can use technologies like native A and replicated data queue managers to do that. But only one instance of that queue manager will be available at a given time. And if it fails, then that's detected by MQ, and the instance is another instance of the queue manager is automatically restarted somewhere else. So again, leader follower pattern. There are some subtleties here, which is what this slide covers, where actually with MQ, it's the queue manager that gets replicated and recovered, okay? And that's done at the queue manager level. And if a queue manager fails, the recovery and failure detection and restart of that queue manager is independent from other queue managers in the MQ cluster, okay? So typically that's something that happens quite quickly. Failures detected, queue manager's restarted, it recovers its logs and it carries on. And because MQ flushes data to disk, that means that you should have a recovery point objective of 0, i.e. you will not lose data or anything committed in terms of, committed to the queue if a queue manager fails. So any in-flight transactions get rolled back, but anything that's been committed will still be there. Kafka has quite a different model. It's the topics that are replicated and recovered across the brokers. And and you make the decision on an individual topic level. So if a broker fails, then the remaining brokers decide who is going to own and be the leader for the set of topics that the failing broker owned, okay? And there's a set of collaborations done by the Kafka cluster to decide how that is and rebalance consumers across the Kafka cluster. And that, for what large clusters, if lots of brokers fail and they had lots of topics that they owned, that takes quite a long time. Also, Kafka doesn't rely in the same way as MQ does on flushing data to disk. Obviously, it eventually gets written to disk, but it's not flushed. It's all buffered in memory. So instead, Kafka relies on in-memory replication to give you high availability of message data or event data. So if you have a wide outage and your entire Kafka broker cluster goes, then chances are data is going to be only in memory and not committed to disk, and you're more likely to lose data if you have a wide outage. Small outages where a single broker goes down is less of a problem, but wide outages are a bigger problem with Kafka than they are with MQ. Both Kafka and MQ have smarts in the application libraries, so not the applications, the application libraries, that allow automatic reconnect to occur and hide that from the application layer. I think it's fair to say that Kafka does more in this space, has lots of options that decide how much the applications see failures. But those options are quite complicated to understand and do sometimes, depending on the decisions you make, result in sometimes events being processed multiple times. With MQ, that doesn't happen, okay? But we don't have as many options. It's much more, we'll hide some stuff from you, but not everything. And, that's more of an application concern, but we will not duplicate those messages. And then I'm going to skip this slide because I think we're basically saying that actually, in reality, we're quite similar. But I wanted to come into topologies once as well. And this is kind of the last set of slides. So, and I think this is really important. This is where I come back to the architectural patterns I was talking about at the beginning. Okay, MQ is all about loosely coupled queue managers running all over the place, and it's up to you how you set those up. And they might, it's possible that you have all your MQ in the same data center, but it's much more likely that you have your queue managers across the whole world. And we do have customers with thousands of queue managers across the whole world, and they route data between them. So that, with this model, MQ kind of comes to your applications, okay? You install MQ where it needs to be, you have applications relatively near to it, and they connect to MQ and then route their data through that MQ network to whichever application it is, wherever in the world they need to communicate. And MQ sorts that out, and it does the discovery, automatic discovery and all that stuff, and automatic routing of messages. Kafka, the model's quite inverted. The applications come to the broker cluster, the Kafka cluster. And it tends to be in a single data center, maybe in multiple availability zones, but tends to be in a single data center. You don't have this wide distributed communication approach that MQ does, because it's all about the data held in the cluster. Now you can move data from one cluster, Kafka cluster to another, but this is duplication of data, it's mirroring of data, but it does allow you to kind of deal with geographical distances if you want to, but it's perhaps not such a common thing with the Kafka as it is with MQ. And then the last point before people start going, of course, there is value to both of this, okay? Some models make more sense with Kafka, some models make more sense with MQ. And the good news is it's perfectly possible to wire these things together and actually have a best of breed technology where you've got an architecture that works for individual applications. The key point is, it is not just a one tool, it's not just a hammer. You don't just need a hammer to solve this. Sometimes you need a screwdriver, and sometimes you need a wrench. Just like with messaging, sometimes you need MQ, sometimes you need Kafka. And hopefully the set of details on this slide gives you an answer to that. Anyway, I've kind of run out of time. Phil, please fill in your session feedback, and over to you, Melvin.
Thank you very much, Matt. That was very rapid and very useful session. Please give feedback. It's very important to us. And once again, thank you, Matt, for another brilliant session.
No worries. And if anyone has questions about this, again, you can reach out to me on my email address. Happy to have another conversation.
Thank you. There aren't any anything in the chat room.
No, I think I've given them stunned silence.
So I'll say goodbye and thank you for attending, and thank you, Matt.
Thanks. Bye now.